Our project was on the Chuck-a-Luck game. In Chuck-a-Luck, a player places a fixed bet of $1 million against the house on an integer n between 1 through 6 and rolls 3 dice. If one die lands on the integer n, then the player wins 1 million. If 2 dice land on n, then the player wins 2 million. And if 3 dice land on n, the player wins 3 million. If no dice land on n, the player loses $1 million. For each playthrough, the player repeats this process 30 times. The purpose of this probability experiment was to determine the theoretical and experimental probabilities of each individual outcome, along with the average amount of money gained by the house.
All right, so for the theoretical data, this particular experiment had either a success or fail outcome. It consists of a fixed number of 3 independent observations per play and has an equal probability of success for each observation. Therefore, this experiment meets all the requirements for a binomial setting and distribution. Since the experiment meets those requirements, the first 4 theoretical values were calculated using the binomial probability equation, as you can see on P lose to P3 wins. And the last probability, P win, was found by subtracting P lose from 1, since there can only be a success or fail outcome overall. However, P win can also be found through the cumulative probability calculation, since it's combined, since it's a total of the combined or added outcomes of P1 win, P2 wins, and P3 wins. Along with this, we calculated the average house net gain. Using that, that's the same thing as finding the mean, which is the total number of plays times the probability of that occurring. And that was calculated by subtracting P win from P lose to determine the overall probability of gain for the house, which is 0.158, and then multiplying that by 30, since each player performed 30 trials in the experimental portion. And that resulted to 4.74 million every 30 plays. And then the standard deviation was calculated by finding the square root of the mean times 1 minus the probability. And that resulted in 1.998 million for every 30 plays.
Alright, so the actual data that was gained was our experimental data. And the first table here describes how many times each outcome came up. So, for example, Chris lost 19 of his 30 plays. The next table here describes the probability of each outcome. And this is a pie chart representing the average experimental probability distribution of all of our values for each player over the 30 different plays. And when comparing them, the theoretical values are, as Chris described earlier, shown here. And then the experimental values were determined down here. And you can see the slight differences, as in no one actually wins 3 times. And we can see the slight differences along each of the probabilities and their actual outcomes.
So in conclusion, we learned that the application of theoretical probabilities to gambling can lead to accurate experimental results in the long run. So this works with the law of large numbers really well, because the experimental probabilities became closer to the theoretical probabilities after each play. And if more trials were conducted overall with the experiment, then the experimental values would become much more likely to come closer to the theoretical values. And the experimental probability for a loss was greater than the theoretical, while all the experimental probabilities for different types of wins were less than the theoretical ones. But despite this, all the respective values were fairly close and completely reasonable given the sample size of the experiment. Also, the data collection method of the 3 players rolling the same dice could be biased in the fact that each individual had a slightly different rolling method. However, the data gathered was real and consisted of completely randomized outcomes, so the only improvements that would fit the experiment would be an increase in sample size.